Well, distinguished colleagues, it's February 4th, 2 p.m. Moscow time, the year 2022. And we're beginning the panel session for the defense of the thesis by Ivan Giba. The thesis is submitted for the academic degree of candidate of sciences in physics and mathematics. The specialization is 136 optics. The topic of the thesis is NMR diagnostics of hydrogen bonds in complexes of phosphinic and phosphonic acids. Under the order issued by the Academic Secretary of St. Petersburg State University, Alexander Gnatov, as of October 27th, 2021, number 10286/1, I, Doctor of Science in Physics and Mathematics, Konstantin Takhadze, Professor, Head of the Department of Molecular Spectroscopy of St. Petersburg State University, was appointed the Chairman of the Board. The order also approved the members of the board, and I would like to introduce them. They all are working remotely today, by the way. So, Nikolai Filipov, so pleased to see you. Vladimir Chizhik, here, I'm here, okay. Yes, we see you all. Oleg Filipov, here as well. And Alexander Filerovsky, the most remote participant from Poland. And our candidate for the degree, the main person for today, is Ivan Giba. Hello. And we're also pleased to welcome the thesis supervisor, candidate of Sciences in Physics and Mathematics, professor of the Physical Organic Chemistry Department of St. Petersburg State University, Pyotr Tolstoy. Hello. And I would like to inform you that the panel session of the Dissertation Board is being recorded and broadcast on the St. Petersburg State University website. And our panel session is also interpreted from Russian into English, or vice versa, in case we have some such questions. And where is this email address? Oh, on the page with live broadcast, we have an email address, and all listeners can submit their questions to Mr. Giba online, and the questions that have nothing to do with the scientific discussion or the text of the thesis, and also anonymous questions, will not be voiced. Under the order on the procedure of granting academic degrees at St. Petersburg State University, approved by local regulatory acts of St. Petersburg State University, we'll call it order later on, the session of the Dissertation Board is valid, providing 2/3 of the appointed board members are present. We are 5, so 2/3 from 5. And the total number is not to be fewer than 4 people. Yes, so they calculated it accurately. And everyone from our dissertation board is here today, and I am here offline, and 4 members of the board are working remotely online, so we have the quorum. And I ask the member of the Department of Dissertation Board Support to fill out the attendance list. As for our today's agenda, it is as follows. First of all, it should not last more than 2 hours, and first we're going to hear the chairman's presentation about the documents submitted by the candidate for the degree. and the conformity with the requirements. And I will reply. I will answer the questions if there are any. Then the candidate's presentation providing an overview and findings of the research. 15 minutes for that. Then questions to the candidate regarding the presentation, 2 minutes per question, and 5 minutes for all the questions. Then the chairman's report on the thesis, 10 minutes for that. The candidate's comments about the report on the thesis and replies to the questions to all. Yes, I missed it. The reports on the thesis will come first. The board members will be taking the floor in turns to provide their reviews and questions. Then we're going to have an open discussion. And don't forget to... Oh. So if we have some guests, yes, if there are any guests who want to participate in the discussion, don't forget to state your full name in the registration list. Then the chairman will ask the questions submitted during the broadcast via our website. And I would like to draw your attention to the fact that questions that will take more than 10 minutes to read out will not be voiced, so don't submit some full reports, please. Then the chairman will ask the questions submitted during the broadcast. Yes, as I've already mentioned, some long questions will not be asked. Then the candidates replies to the questions. Then we're going to hear the presentation of the candidate's thesis supervisor. Then we may have a 5-minute discussion before the open balloting on conferring or non-conferring the academic degree. The discussion of the results of the defense is not broadcast. And then we're going to have open balloting, count the votes, and record the results in the protocol. Afterwards, we're going to make a decision on whether to confer the academic degree to Mr. Giba or not. And finally, we're going to listen to the candidate's closing speech. Distinguished colleagues, if there are any questions to the order of our session, feel free to ask them. If there are no objections, let us start. First of all, I would like to ask you to turn off the sound on your mobile phones. Yes, put them over here. So I start. First of all, the chairman's presentation. The thesis by Ivan Giba for the academic degree of Candidate of Sciences in Physics and Mathematics, the specialization 136 Optics, is titled Nmr Diagnostics of Hydrogen Bonds in Complexes of Phosphinic and Phosphonic Acids. The thesis was approved for the defense by the order of the Academic Secretary of St. Petersburg State University as of October the 5th, 2021. I won't give you the numbers. Ivan Giba has prepared his thesis at St. Petersburg State University as a postgraduate student. And I've already introduced his thesis supervisor, Petr Tolstoy. 3 published works describe the research findings. All these articles are published in journals indexed in Web of Science and Scopus. And all the documents submitted by the candidate for the degree, as far as I'm informed, comply with the St. Petersburg State University requirements, and they are found in the certification file of the applicant. And curator of the defense member of the Department of Dissertation Board Support has all the copies. And before I give the floor to our candidate for the degree, I would like to ask the members of the board if there are any general questions to the candidate for the degrees. They need to consider the whole list. The whole list of documents submitted by the applicant. No need for that. Does everyone support that? Yes, we agree with that. No questions. Okay, so Ivan, please, you have the floor. Distinguished colleagues, good afternoon. First of all, thank you very much for the introduction, and let us start. For the welcoming remarks, yes, okay. Compounds that have proton donor and proton acceptor groups are capable to form complexes with hydrogen bonds. The geometry of the formed complexes can be described using the distances between heavy atoms and bridge proton, or their linear combinations. In order to study such complexes, especially in non-ordered environments, we use spectral analysis methods such as fluctuation spectroscopy, electron spectroscopy, vibration spectroscopy, and Nmr spectroscopy. There are spectral parameters that are interpreted in the terms of hydrogen bonds using the correlation ratios. And on the slide you see the references to the works that devise methodology of using Nmr spectroscopy for complexes of a different content. And one of the advantages of Nmr spectroscopy is the set of spectral parameters that can be used to establish the geometry of hydrogen bonds. And above the shift of bridge proton, there are some useful characteristics like chemical shifts of heavy atoms that form hydrogen bonds, neighboring atoms, and also the constants of spin-spin interaction. However, the study of complex formation using spectral parameters of phosphorus atoms is still not very well studied, regardless of the fact that phosphorus atom has a range of beautiful parameters that can be used to conduct measurements using Nmr spectroscopy, like 100 content of phosphorus isotope, spin quantum number of 1/2, and gyromagnetic relation that is quite high. And as a study object, I've chosen two types of acids, phosphinic acids, namely dimethylphosphine and phenylphosphine acids that have one OH group, and phosphonic acids, tert-butyl phosphonic acid that has two OH groups. And the goal of the work was to resolve a reverse spectral problem to define the structure and characteristics of non-covalent complexes using Nmr spectra on phosphorus nuclei. The goals were as follows: to study the structure of molecular complexes of phosphinic acids with substituted pyridines and describe correlation dependencies of the changes of chemical shift of phosphorus from the change of geometry of hydrogen bonds, and also to establish the structure of self-associate of tert-butyl phosphonic acid and complexes of tert-butyl phosphonic acid with bases. In order to exclude the complexes, we used a liquid Nmr spectroscopy, and the solvent was used as a deuterated liquefied freon gases. And we needed it to conduct experiments at low temperature up until 100 Kelvin. And this allowed us to increase the lifespan of complexes, and in slow exchange we registered the signals from individual complexes considering the stoichiometric distance and content. And to that end, the freon gas mixture gives us very nice characteristics: low freezing temperature, good solubility of compounds, and spectral purity. So let us start with dimethylphosphine complexes with bases. And the content of the sample was chosen for every complex, so that the only intermolecular complex in the solvent was the complex of 1:1. And when we increased proton acceptor capability of the bases, the chemical shift of bridge protons went to the weak field, past the maximum, and then got back to the strong field. And what's characteristic for the complexes with reduction of hydrogen bond, the transfer of hydrogen via the center, and the shift with the formation of sweeter ion complexes. And using the well-known dependencies between the bridge proton position and proton shift, knowing the chemical shifts for all of the complexes, we can define the position of this bridge proton, and we can demonstrate it by Q1 value, the distance from the geometric center of the bond to the proton. And thus getting the value of Q1 and defining the value of phosphoric shift, bridge shift, we can draw a correlation between the position of our values and approximate it with two asymptotics. One is free acid molecule and phosphonate anion. Similar works were conducted for phenylphosphinic acid complexes with bases, but as this acid is a stronger donor for the proton, the majority of complexes that we see on the screen have sweeter ion structure. And the results that we got, we processed and summarized them like that. If instead of absolute value of phosphoric shift we use shear from the change with full protoning from POH to PO minus for dimethyl phosphinic acid, where the chemical shift changed in the range of 15 millionth, and for phenylphosphinic acid, where the shift was changed by 5 millionth of percent, we can draw one correlation dependency with a change of distance of OH during complex formation. And here delta R is the difference between OH distance in the complex and the distance of OH in free acid monomer. All the dependencies that we observe, they coincide well with the curve positions, except for 2 and 2,6 of substituted pyridines. That pushed us to study the underlying causes, and that is associated with the fact that, except for proton donor group of OH in acid molecules, we also have PO group that can be and proton acceptor and participate in the formation of additional hydrogen bonds. And the assessment of contribution of both of these factors into the value of phosphorus chemical shift was conducted by quantum chemical calculations. We shifted the proton via the center of hydrogen bond and also conducted the rotation of pyridine ring to break it down and form an additional PO bond. The change of chemical shift of phosphorus during the shift of proton via the center of bond is demonstrated by dimethyl phosphinic acid complexes with pyridine. For other complexes, the results will be quite similar. The shift of proton was conducted quasi-adiabatically. We fixed all the steps and other parameters were adjusted. When the bridge proton went through the center of the proton bond, we saw the change as we planned to see it. The change through the maximum and chemical shift of phosphorus was changed in a sigmoid manner. Similar results were previously fixed in our experiment. And in order to describe the influence of additional PO group on phosphorus, we compared two complexes, acid with pyridine and complex with collidine. As for pyridine, during rotation we see the formation of additional bond with CH proton in ortho position. During the rotation of pyridine, this bond breaks up. That causes not just the maximum for energy of 12 kilojoule, but also strong changes of phosphorus shift. As for collidine, that has no CH group, we have the weak bond as well, CHO, but with metal group in ortho position, and this bond is much weaker, as we see based on the graph. Therefore, the change of energy is smaller, and the chemical shift is smaller as well. Thus, we see that the shift of chemical shift of phosphorus to the strong field of 2 to 6 with substituted pyridines is explained by the fact that we have additional hydrogen bond with PO group and dimetal in order position, and we also have the impact during the rotation of pyridine ring on the phosphorus shift. Unlike phosphinic acids, phosphonic acids have two OH groups. Thus, they are capable to form complexes of more or complicated content, both in self-association and in complexes, in cases of formation of complexes. So, self-association, based on the spectra that we obtained for third-butyl acids, phosphonic acids, we can draw the following conclusions. First of all, in proton spectrum, we see two signals that, using constant of phosphorus, they break down like that. Second point is that in phosphoric chemical shift, we see one signal. Thus, we can make a conclusion that all the nuclei of phosphorus are chemically equivalent here. The most simple complex that is responsible for all these spectral requirements is the tetramer. The formation of such a tetramer can be drawn like that, as two cyclic dimers. Each of them has a free PO group, and during approximation of these groups, PO interacts with lone pairs. PO, POH, they start interacting with the PO group. This structure is easily reproduced by quantum chemical calculations. And if we take away third-butyl groups, we can see that all the phosphorus nuclei form this tetrahedron. And we form a cell of 4 molecules associated with 7 hydrogen bonds of medium strength. And this complex is stable not just in the solvent, but it is also not flexible conformationally. And when we added collidine, self-associated was destroyed, and several complexes with different content were formed. And we analyzed relative intensities of isotope effects and quantum chemical calculations to establish the stoichiometry of these complexes. The complex with the circle is the most simple complex, and TOH bonds are involved into the formation of complexes with bases. And as for the star complexes, there are 2 different isomers, T21, where a cyclic dimer of phosphonic acid forms hydrogen bonds between the residual OH groups and base molecules. If we talk about complexes with 1 molecule of acid, we see 1 signal, and in partial deuterization, it forms yet another additional signal in the strong field. And thus we can make a conclusion that that's the complex with 2 cooperatively interacting hydrogen bonds that are equivalent in the NMR scale. And the complex that coincides with all these requirements is a complex where 1 proton is taken to hydrogen and another one stays in acid molecule. And we have this shift transition, pronounced transition. And here, both bonds, OH and are zwitterions that stabilize hydrogen-bound d anion. That is, according to quantum calculations, is a metastable complex. Thus, summing up, I can conclude that the work provides a new correlation that binds the change of distances of OH with the change of phosphorus shift in complexes of phosphinic acids with substituted pyridines. We established the contribution of the position of a bridge proton and the rotation of pyridine ring around the axis of hydrogen bond into the phosphorus shift value, and we established the structure of self-associated of third-butyl phosphonic acid in the solvent with a proton polar solvent, and tetramer is formed, and we established stoichiometric contents of third-butyl phosphonic acid with collidine complexes, and we fixed metastable D9 that is stabilized by hydrogen bonds with bases. Thank you so much. Any questions? Yeah. Questions. to you, Ivan, on the report. Questions on the report only. Can you flick to slide number 3? Yeah, this one. Yeah, third one. No. Pardon. No, that was slide 5. Beg your pardon. Yes, you stated here about the characteristics of the solvent, the spectral purity, transparency in the field of observed signals. I don't get it, don't get this wording when we talk about NMR, because what do you mean here using this wording, spectral purity? The transparency for NMR method is secondary or insignificant, so to say. Could you please specify what you meant here? The solvent signals in proton spectrum are in the range from 5 to 8 ppm, whereas the signals from complexes that we observed, including the complexes of phosphinic acids with bases phosphonic acids, are in the range of 10 to 20 ppm. So that's what I meant. So actually you mean that there is no overlapping of these lines with the solvent? Yeah. That's it. Thank you. Any other questions? Well, I would ask one. Yeah, sure. Slide 9. Yes, the 9th one. Next one. Yeah, this one. For some reason I have wrong numbers, page numbers. So over here, could you please tell me, some lines associate well with your correlation dependency, and 10, 6, 8, 7, 9, they are somehow left behind. So these signals are strongly different from the correlation dependency. Could you please explain it? The signals that draw out, these are the signals for 2 and 2,6 substituted pyridines. As it was mentioned on this slide, we conducted an assessment of this association. We rotated the pyridine ring and established that this shift of chemical shift to the strong field for phosphorus, over here, yes, in cases of 6 and 8 complexes, for monosubstituted pyridines, and for 7 and 9 for di-substituted in order position. So it is associated with the formation of bond with a methyl group in order position of pyridine. Do I get it right that your correlation dependency here is useless for this class? Why? We have a difference of 1/2 millionth percent that is quite nearby. Well, nearby, you know, is a quality characteristic. You know, depends on how you judge it. Yeah, tastes differ, you see. And, you know, they do not show some correlation with the graph, and you require some additional words here, some restrictions here, to my mind. Yes, they moved a bit, but they are still in the general trend. Yeah. Okay. Let it be. Taste really differ. Okay, thank you very much for the answer. Other questions? Okay, none. Okay, now I'd like to give the floor to the members of the board. So you can answer all questions at once. All the questions are after every speech. So, Ivan, you can choose the most convenient option. So, any questions to our speaker? Do you offer to read out straight away? I thought that questions will be asked, first of all. Oh, okay. So, gentlemen, let's go in turns, as you wish. I have Mr. Filipov, first of all, Nikolai Nikolaevich, then Oleg Andreevich, then Professor Filerovsky, and then my review, and Professor Chizhik as well. So, Nikolai Nikolaevich, you come first, please. So, the work is dedicated to the study of the structure of molecular complexes of phosphinic and phosphonic acids based on Nmr spectroscopy. Regardless of the rich history of study of hydrogen bonds, today we see significant interest to the study of complexes of phosphorus-containing compounds. However, stoichiometry and the construction of associates with the participation of phosphinic and phosphonic acids, including aprotonic environments, they are poorly studied. And in this case, this work makes a contribution to the study of hydrogen bonds, and it is quite relevant. The thesis has 4 chapters, the list of literature sources, and language is quite clear. And I've seen an English copy. I won't read out all these descriptions of sections because everyone is aware of that. And these descriptions are given in overall the thesis is quite impressive, and we got a range of interesting results. The high level of experiments guarantee the credibility. And on the topic of work, there were 9 reports made at international conferences, and 3 articles were published in leading journals that confirms the importance of the results. And I believe that the thesis corresponds to all the requirements. And I have 2 questions to the author. The first question. For complexes with content 1:1 of phosphinic acids with pyridines, I would like to ask if you have experimental demonstrations of the presence of proton tautomerism between molecular and Switterian forms of hydrogen bond of OH, and at least for most strong complexes in this series. And the second question, for the complexes of phenylphosphinic acid, is it possible to define geometry of the hydrogen bond of OH-N using the value of the chemical pH proton shift or the constant of spin-spin interaction in the pH group? And that's basically it, what I wanted to ask. So the first question. The presence of a proton tautomerism could be defined using several parameters. That's chemical shift of nitrogen atom, or using valency vibration on the group. Unfortunately, these criteria were not analyzed in the work, but if proton tautomerism is present, then the distances that we established in the work would relate to two tautomers. And as for pH constant, yes, we observe pH constant in the pH spectrum. It makes up 600 Hertz, and it is changed during deprotonization for several hundreds of Hertz. However, the chemical shift of the pH group is found in the area of aromatic protons, both for the cases of phenylphosphinic acid and bases for the aromatic group of phenyl. Therefore, the signals overlap, and in practice, we can't use this chemical shift of the pH group. Okay, thank you. I'm satisfied with the answer. Other questions? Nikolai? No, I had no other questions, and I'm fully satisfied with the answers. Okay, then, Professor Chizhik. Vladimir, your questions. I would like to specify my review or my questions? Well, your review. Yes, you already had questions. Yes. Yes, I've already asked them. There's no need to read the full review. Yeah. I believe the need to provide a review for this work leads us to certain repetitions. Therefore, I'll try to dwell upon the points that are not quite obvious, so I'll omit those that are quite obvious. As I've already submitted my review, it's already downloaded on the web page of the applicant, so the work is written on a very relevant topic, and it covers two integral components: the general issues of further understanding of regularities of hydrogen bonds that are of paramount importance in nature, because hydrogen bond in water defines the opportunity for life development on Earth. And second point is that it provides answers to particular problems of phosphorus-containing compounds that were chosen as objects of study. The relevance of this work is defined by the fact that both of these factors are really integral. And in my review, I mentioned it that in 2011, an article was published by 14 authors from 8 countries in applied chemistry, and the article discussed the novel definition of the hydrogen bond. It's titled "Defining a Hydrogen Bond." So these questions regarding the fact that hydrogen bond is something that we've known for 100 years already, still a lot of questions remain that require specification. Therefore, this work is quite relevant and fascinating. And overall, it's well structured. And now I go from one section to another. The introduction provides the relevance description, the relevance of objects, of the choice of objects, and also provides the description of methods of study. The goals are formulated, so everything is okay. And then the review. In the review chapter, the author demonstrates good knowledge of information on the current state of studies of hydrogen systems. And he writes about the trends, about the problems for development, and also he makes an emphasis on hydrogen-bound complexes of phosphinic and phosphonic acids. that are the study object. And here it looks quite well, quite impressive. And unfortunately, Ivan Giba ignored the works of outstanding Russian scientists Nikolai Sokolov, Vladimir Ulyanovskaya, and Maxim Buxon. That's a pity that that's a huge volume that he omitted. The main achievements of the author are reflected in chapters 3 and 4. And here the author resolved a range of specific problems. And here I'd like to mention that when writing this work, the author demonstrated the universal approach that's quite a labor-intensive procedure of preparing the samples. That's quantum chemical calculations, that's Nmr Spectroscopy skill. So that all demonstrates that qualification requirements that we have for the applicants, they are met. Yet, I would like to mention the following fact. The author uses a particular way to reduce this exchange speed in the studied objects so that spectral lines gave better resolution. And it is quite an old method, and it was actively used in works of his thesis supervisor, and even before some works used this approach. So it's still relevant, and that's an interesting aspect of work. But what should we bear in mind is that at that hydrogen bond and spectral characteristics are studied in exotic environments. In this regard, the results of work, well, I would say that these results can be circulated for more relevant systems that contain water and spectral solvents and so on, where exchange processes are quite quick. The fact that hydrogen bond of these objects meets the same regularities, I believe that's an open question. And as for the results, they were presented quite well in the presentation, but I would like to mention that most interesting results were given in chapters 3.3 and 4.3 that described self-association of tert-butyl phosphonic acid and intermolecular complexes of tert-butyl phosphonic acids with collodion in proton solvents. So I'd like to emphasize that that is done in specific conditions. The proofs are quite interesting for new structural ideas on the complexes like this tetrahedron that the author demonstrated and described with all these SAID bonds. So this structure is of interest. Overall, the work creates a very good impression, but I would like to mention the following fact. In the text of the thesis, the author lacks provisions that were particularly offered for the defense, that it does not allow us to understand the claims, so to say, of the author, because the author should have claims for novel results. And it's clear that in conclusions we can see this positions that can be seen as provisions for the defense. But here you see a lot of morphology results, so therefore, these provisions are quite vague. They're quite vague. So that's kind of. So we see a kind of possibility for discussion here. So essentially, in the structure of the thesis, we don't see this provision specifically. So the language is quite good, though there are some style and grammar mistakes that any work has. Overall, I believe that we could avoid these problems, like energy of kilocalories per mole or kilojoule per mole. So that's incorrect. And in tables, you have a lot of valuable figures, 5 or more, so that's not important for physics. And on images, it would be nice to see the confidence intervals. It would allow us to assess the credibility of some or other materials. However, these comments do not compromise the novelty and importance of the results, and my assessment is quite positive about this work, and I believe that Ivan Giba performed a high-quality and holistic research, and he made a good contribution to the understanding of hydrogen bonds in phosphinic and phosphonic acids and proton polar solvents. The results of work were published and tested at different conferences. And my conclusion is as follows. The thesis by Ivan Giba, titled Nmr Diagnostics of Hydrogen Bonds and Complexes of Phosphinic and Phosphonic Acids, meets the requirements of the order as of November 19, 2021, on the procedure of granting academic degrees at St. Petersburg State University. And our applicant deserves the academic degree of Candidate of Sciences in Physics and Mathematics and specialization 136 Optics. And to my mind, we still need to discuss this attribution of this work to specialization optics. And as for Articles 9 and 11 of the above-mentioned order, they are not violated. That's it. Yes, Ivan, do you want to answer? Yes. Thank you so much, first of all, for your review. I accept the criticism. Certainly, I should have paid attention to domestic scientists, and I should have worked more on the text in order to make these claims obvious, claims that I make. And as for the issues of exclusivity of results, neuterated freon gases, here I can say that as we sorted out, the correlations issues can be always open for discussion, and we can specify the answers all the time. But still, I agree that when we change the type of solvent, the structure and of complexes will change, and will change the solvents, thus changing the structure of complexes. The geometry change, however, as well as chemical parameters change, will stay the same regardless of the type of solvent. This is indirectly supported by the fact that the change of chemical shift of bridge proton, both in vacuum and in different spectra for a range of complexes, always go through the maximum, have similar dependencies. So that's what I actually studied. And as for the specialization, the choice of specialization, there are scientific and administrative reasons. I'll go upon the scientific ones. I considered fundamental issues of molecular spectroscopy namely correlation dependencies, used to describe the hydrogen bonds. And these approaches are applied both for optic spectroscopy and for Nmr spectroscopy. And in my work, we took into account the frequencies of vibration quantum chemical calculations when we defined the structure of the complexes, and also we analyzed quantum chemical calculations and vibrational frequencies and PO impact on the complexes. Although, as these results were not supported by experiments, they were not included into the work. That's it. Okay, thank you. So, yes, I have no other questions. Okay. Now I give the floor to Oleg Filipov. Yes, I won't read out everything, if you don't mind, but the main objects of study are hydrogen bonds formed by acids based on phosphorus. And regardless of the fact that these are quite interesting objects for hydrogen bonds and they are long studied, it turns out that you still have a lot of options. And from my point of view, I can say that phosphinic acids were the object on which dihydrogen bonds were considered in 1936, though, and 60 years passed before these bonds were recognized. Still, this subject is of paramount importance. And basically, it should be studied in details, in doctoral thesis, and in other works. So that's a classical work, the introduction, literature review. Everything is written quite well. In the literature review, we have detailed consideration of peculiarities of complexes that are formed by study objects. And I really liked the detailed experimental part that is written quite in a reproducible manner. And I won't read out all these points, but I would like to stress what I liked particularly. I like the tetramer of tert-butyl acid. It's really a novelty, and it is very well described. And I also liked the anion dimer. That's also a thing in itself, and when you demonstrate such a thing to anyone, the person says, are you crazy or something? You won't have an anion dimer. There should be an ion couple. And in my time, I found a similar dimer for D-anion, which caused a lot of discussions. And Ivan demonstrated that the structure of this complex should be like that, and it is based on NMR data and quantum chemical calculations. I had some critical comments, mostly chemical ones, not physical ones, because I represent chemistry here in this board. So, the first question is, why didn't you use those devices that are recommended to calculate the chemical shifts? Maybe for phosphorus it's not the same, but for other substances it's like that. Then, in pyridine 12, you have the second center that is based on pyridine. That's not commented, and you don't have a table of how you used the results for analysis. I've already praised the detailed description of approach, but As for the methodology of consideration of the solvent, it is written quite poorly and you don't understand the parameters that were used. Did it vary epsilon and what were the basic parameters? In ordinary models, it is we should really use the exact characteristics for protons. And as for the tetramer, you don't discuss the Gibbs energy. It's really an important entropy factor that can't be ignored, but you wrote nothing about it. In your work, though, I found this data in an article. It looks a bit strange. Then, ketame analysis. This question is associated with the energy of the second CHO interaction in these molecules. And this interaction is somehow balanced with the main interaction. The main interaction and additional interaction, they are 1.5 times different. And this interaction with methyl group in automethyl substituted groups, it does not drop significantly. So it's not quite clear here why it happens, why it's so strong, and why it weakens poorly. Maybe these are the cyclic structures, resonance structures effect, like those that are formed in nucleotide couples of DNA. Yeah, it's a bit more simple than that. And the last question that is associated with the same issue, the barrier for automethyl substituted pyridines is lower, and I had an impression that methyl group there can stay in binding with oxygen throughout all this rotation cycle, or maybe it shifts at minimal distance and it breaks down at minimal distance. Maybe it goes like that. So these are the chemical questions, indeed. But it's interesting to discuss them, and certainly they don't influence the overall high mark. The results are quite credible. They are based on huge experimental study using state-of-the-art methods, and interpretations are done at high level, and judging by the results, we've seen 3 articles in good journals indexed in Web of Science, and the reports were delivered at 9 conferences, and it demonstrates high level of this work. Thus, the thesis by Ivan Giba, titled Nmr Diagnostics of Hydrogen Bonds and Complexes of Phosphinic and Phosphonic Acids, meets the requirements of the order on the procedure of granting academic degrees at St. Petersburg State University. And Ivan Giba deserves the academic degree of cognitive sciences, physics and mathematics, and specialization optics. And Articles 9 and 11 of the above-mentioned order are not violated. So, is that it? Yes, that's it. Okay. You want to answer? Yes, yes. Yes, I agree with these remarks. We have Gibbs energy here, and the value of PC for bases were given in scientific publications, but unfortunately I omitted them in the thesis. As for Igla bases, in the work I have a part where I carried out comparisons for different bases. And conducting such comparisons, I made a conclusion that using more accurate bases gives us a specification of absolute values, but they have no impact whatsoever on the correlation dependencies. If the shift of phosphorus goes to the strong field in one basis, it shifts over there in another basis as well. Therefore, the choice that we made was also quite accurate. for the goal, and they did not require a lot of computational possibilities. And as for dimethylpyridine and its center, in the works that were also dedicated to the study of hydrogen bonds in different donor proton groups with dimethylpyridine, in all cases, this bond was formed with nitrogen that has a couple. And as for the methods to take solvent consumption into account, we used polarized dielectric using chloroform molecules. Theta changed from 10 to 100, and this was calculated in the model of continuous polarized environment. As for Q-time calculations, everything is much more simple. That was a misprint. I've written kilojoule, though it was kilocalories. And as for PO bond with methyl in order position, indeed there's no breach of bond that happens here. It happens only during the rotation of pyridine, this bond with other methyl group. And this is proven by the analysis of the sum of Van der Waals radii. So I agree with this comment as well. This bond remains here. I hope I answered all the questions. Did I? Yes. I'm really glad that I've asked all these questions. And the only comment on the basis, in such a case when you don't need to use heavy bases, you may take 31B. Yes, it's too simple for that. Yes, but it will also work. Yes, because the trans won't change. Yes, that's it. Okay, other questions? That's it. All the questions were answered. Okay. Okay. The next board member is Professor Filerovsky. Well, I'll be brief, because my colleagues have already mentioned it all. They demonstrated that the work is pretty good and quite outstanding. The good complexes were chosen and studied using good methods, applicable methods, and that allowed to measure the position of this proton, because in polar environments we're going to have such a broad range that you won't be able to measure the correlation. And as for the phosphinic acids, and as for the deviation from the correlation, the effect is associated with the fact when you don't have a methyl group, we have a bifurcation shift of proton, and bifurcation bond is formed, and there is interaction with NH group. And when you have methyl group, then this and then we see the prevention of this bifurcate hydrogen bonds formation. Therefore, it will be more linear, a more linear bond, because the second group of PO won't be observed here. But these are the general comments. Overall, everything is quite good, and you can always find some other ideas to study. For example, the change from freon to water solutions. But at some point, you just need to stop to sum up everything and to finalize all your results. Therefore, I believe The results are pretty good, and I have no doubts about the fact that Ivan deserves the degree of candidate of sciences. Do you want to answer, Ivan? Yes. Yes. I need to check all the provisions that you described. Thank you so much for the review. Okay. Are you satisfied? Yeah. Yes. For sure. So Alexander is satisfied. So that's just me who's left. So all the issues that emerged during the discussion were already discussed here. So I would like to emphasize one point. Spectral parameters that allowed us to study the complexes can be presented by the frequency of PO oscillation. So we move to lower frequencies. And my question is as follows. Did you study the change of frequency of this fluctuation for the entire series of complexes during quantum mechanical calculations? And what's the accuracy that you have to define this distance from heavy atoms to bridge protons? In your calculations, I'm not talking about the measurements. Overall, this is a finished study, and the author managed to obtain quite valuable results. And I should mention that the thesis of Ivan Giba meets the requirements of the order on the procedure of granting academic degrees at St. Petersburg State University. And Ivan deserves the academic degree of candidate of sciences in physics and mathematics in specialization optics. Yes, optics, and I emphasize that. And I believe we can not but mention this inconsistency of attributing topics to specific specializations. We need to develop the topic because we have an overlap here of chemistry and physics and some particular specializations in optics and so on. And I've been working with optics for all my life, but I beg your pardon, I don't know about aberrations that exist there. In some optic system, we are working with hydrogen bonds, but it's really hard to attribute this study to the optics science, though we understand what you're talking about. So these inconsistencies do not influence the high quality of the work, and the author demonstrated good skills, good experimental skills, not using optic methods, but still using NMR resonance. And this work is a finished study, and the author managed to obtain fascinating and valuable results. And I believe Ivan Giba deserves the academic degree of the candidate of sciences in physics and mathematics, based on all the requirements. That's it. That's what I wanted to say. Thank you so much for the review. As for the fluctuation frequencies of PO group, we analyzed them during the work. They change by several reciprocal centimeters. during the transition of molecular complexes to zwitterions, but unfortunately during the work they were assessed by quantum chemical calculations. I don't have experimental proof for that. And as of today, the work is ongoing, and the lab of non-valency interactions team is still working on that. As for the error, I believe it's some 500th of a hundredth of angstrom. That's it. So, distinguished colleagues, distinguished members of the board, is everyone satisfied with the answers and the discussion? Yes, I am. So I believe everyone else is satisfied as well. Okay. So then I have a question to everyone present here. So maybe you want to comment on the work, and I can give you no more than 2 minutes for that. And we can also have some questions that were submitted during the broadcast, yes, via our website. Do we have some external questions? Okay. So, Piotr, could you please tell us about the author? Once again, hello. I'm pleased to welcome all the members of the board, and it's really a pity that those people whom I realize did not manage to come, Alexandrovich, Alexander Ivanovich, and I hope that soon we'll be able to see each other personally offline. Let me tell you a few words about Ivan. I've known Ivan from the master's course, and he had a master's course at Chemistry Institute, and he worked on self-association of phosphinic and phosphoric acids, and these results were published, and 2 articles were published in Q1 and Q2 journals. And as for the experimental part of the thesis, it was performed at the Chemistry Institute, and this is associated with the fact that Nmr spectrometers are located there. And during the PhD course, Ivan mastered a low-temperature spectroscopy technique, and then he trained other students in synthesis of freon gases and sample preparation using high vacuum technique. It's quite complicated, and it's quite a demanding technique, and not everyone copes with it well. And for me, characteristic for Ivan is that in the previous decades in German universities in Greifswald and Regensburg, they try to use our example to organize such a low-temperature spectroscopy of NMR in liquefied gases, but for some reasons they did not finalize this work. Therefore, this method today is something that just St. Petersburg State University has. And the experimental part of this work and quantum chemical calculations were performed independently by Ivan, and he was quite diligent and insistent. And as an example, I can tell you that after the thesis was written and submitted, regardless of the fact that further career of Vanya is unlikely to be associated with the university, still Vanya with colleagues prepared a draft for the 4th article on the thesis. And together with these studies, Vanya started working at R&D in biopharmaceutical companies, and he specialized in certifying research laboratories, and Vanya is developing quite well here, and now he's head of quality department at Garafarm. And I believe that's not the limit for Vanya, and further on, I hope that he will continue his professional growth. And getting back to the PhD studies, I would like to mention that Vanya got a Russian Foundation for Basic Research grant. He was participating in other grants as well. And overall, I'm happy that Vanya finalized this work and published the results, and I wish him all the possible success. That's it. Thank you. So the following question to all the members of the board and to Ivan. Does any of you have any comments or questions on the procedure? Maybe questions associated with remote access? No? Any questions? None? No. So everyone is impressed. So, distinguished colleagues, before the vote, we can announce a 5-minute break to discuss the results, and this discussion will not be broadcast. Do we need that? No, no need. And if so, let us continue our session. So the opinions should be given independently and publicly. Now it's 16 minutes past 3 Moscow time. Am I right? Yes. I need to say that so to demonstrate that we don't falsify anything. And we can vote straight away, yes, if there's no need for discussion. So 17 minutes past 3. Yes, Moscow time, is it? So we can vote, can't we? Yes, we're not taking this pause. Yes, we're going to vote straight away. So this natural question, whether we award this academic degree of candidate of sciences in physics and mathematics to Ivan, and we're going to have an open balloting right now. Nikolai Filipov. Yes, I vote for the award of the academic degree. Vladimir Chizhik. Yes, I also vote for the award of the academic degree because this work is a qualification work. There are no doubts in the qualification of the applicant. Yes, as for the attribution question, we've already discussed it. So I vote for the award of the academic degree. Okay. Professor Oleg Filipov. I vote for the award of the academic degree. And Professor Filerovsky, I also support this work. So my opinion is that Ivan Giba defended his thesis successfully. Thesis for the academic degree of candidate of sciences in physics and mathematics. Won't specify the specialization, so 5 board members voted for the award of the academic degree, no one voted against it, and no one abstained from the vote. Thus, we award the academic degree of science and the academic degree of candidate of sciences in physics and mathematics to Ivan Giba in specialization 136 optics. So the finalizing remarks, words of gratitude and so on. Thank you very much to the members of the board, to the chairman of the board. Thank you very much for finding time to read my work. Thank you so much for being here today, for all the kind words. And I would like to thank Professor Tolstoy, who worked with me during my master's course, and without his support, without his help, without his patience, and without his analysis of all the results that I obtained, without his help in writing the work and articles, nothing would really happen. No result would be obtained in the master's course during my master's studies and PhD studies. And I would like to thank the colleagues from the lab of non-valency interactions that helped to conduct experiments, to analyze the results, to conduct quantum chemical calculations. And I would like to thank colleagues from molecular spectroscopy department that hosted me during my PhD course, and I would like to thank my wife who supported me during all these experiments, and she still tolerated that all. And I would like to thank everyone who participated in this work, those who are present here today. Yes, that's it. Thank you, everyone. So that's it. Then I close the session. Thank you, everyone taking part in it. Please turn off the broadcast.